Hello everyone, welcome to our capstone project presentation. We are group number 58 and our team members are Sui Huang, Jihao Law and Liang Chen. We are directed by Professor Christian Denner. For this ongoing semester, we have implemented the pedestrian-friendly traffic algorithm with image captioning. With image captioning techniques, it is possible to transfer image data into other forms of data, such as sound, words, or even digital signals. In our pedestrian-friendly traffic algorithm, we aim to improve pedestrian experience at the street level, with a special focus on blind and visually impaired travelers. What we do is to use the computer vision way to deal with different traffic conditions on the roadway. Our project contains 5 parts, which are speed estimation, distance estimation, image captioning, traffic sign detection, and traffic light detection. After having the trained neural network, we can analyze testing images and output detailed descriptive sentence of real-time traffic from the images. With image captioning, we can better generate the language description of real-time traffic conditions. Firstly, we need to implement the speed estimation algorithm, which contains 2 parts. One is detecting vehicles, for which we use a function inside dlib called correlation tracker to track the same vehicle. The other is estimating speed. What we do is to shrink or zoom the image until the width of the row captured matches the width of the picture. Then we can get real-world width from the Google Map scale ruler. The first equation here calculates the displacement of the vehicle between the 2 frames by adding the squares of vertical and horizontal displacement. The second equation uses the displacement of pixels per meter, and frames per second to get.
After we have done the speed estimation algorithm, we have come into the distance estimation algorithm. Just like the speed detection algorithm, we are still using the traditional computer vision way to implement our algorithm. As you can see in the picture, the white vehicle had a distance of 17.69 feet towards us. How did we implement this? First, when you have a known distance and a known width, this statistics coming from the real scenario. With these 2 numbers, we could estimate the focal length with this equation, and then we could use the focal length to estimate our distance. Just simply use the known width times focal length and divided by the meters per pixel. Now we have the distance and the speed of a vehicle. Then we could got a lot of other information. With 2 numbers, we could compute the acceleration speed of the vehicle, and then we could compute if a car could entirely stop before the zebra crossing line, or what kind of speed the vehicle is when they passing the pedestrian. Maybe it is not that important to adult, but it's very important to the blind people or the old people. After we have done the speed detection and distance detection algorithm, we are coming to the most important part of our capstone project, that is image captioning. We use TensorFlow to implement our image captioning. While the image captioning is implemented by a very complicated neural network. The model of the neural network are combined by 2 basic models. The first is image model. We use Inception V3 for our image recognition. Inception V3 is a pre-trained and a small but accurate network, and it is very easy to use in the TensorFlow. Then we need to have our own caption model. That is also the language generator of the algorithm. Like, to implement this, we need to use long short-term memory, because in the implementation we need to generate word by word. Each word are generated by one iteration of the picture and the previous word. So the long-term, non-short-term memory will be very useful in our captioning model. So after we have done this complicated model, we used a very long time to train our uh, neural network with the data set from online resources and taking the pictures by ourselves. Mm, this is a testing result of our algorithm. As you can see, the most accurate result is that a man and a woman are standing in front of a building, like just as the picture shows. Like a man and woman are preparing to cross a street, and on the other side of the street there are huge building. However, like our like program ignores the cars and and more importantly, it ignores the traffic lights and the traffic signs, which is really important in a traffic algorithm. As a result, we need to dump the following algorithms. That is the traffic light detection and traffic sign detection algorithms.
Now we are going to talk about the traffic sign detection algorithm, which we need to localize the traffic sign inside the image and detect the symbol. We used apical data to train the network. In order to pre-process the data, we have 4 steps: shuffling, grayscaling, local histogram equalization, and normalization. There are 2 models we use in the network. One is LENet5 and the other is VGGNet. We print out the plot describing confusion matrix. The confusion matrix is a table that is often used to describe the performance of a classification model or classifier on the set of test data for which the true value are known. From the figure here, the line represents the true value and the points are not on the lines are false value. We observe some cluster in the confusion matrix in the figure. It turns out that the various speed limits are sometimes misclassified among themselves. Similarly, traffic signs with triangular shape are misclassified among themselves. We further improved on the model using hierarchical CNNs to first identify border groups and then have CNNs to classify finer features. The result shown on the right with high accuracy. The result is pretty good here.
Hello everyone, I will introduce the traffic light detection part now. The project was implemented using transfer learning of the Microsoft's COCO pre-trained models and the TensorFlow's objects detection API. The COCO dataset contains images of 90 classes ranging from bird to baseball. The first 14 classes are all related to transportation, including bicycle, car, and bus. And the ID for the traffic light is 10. For the API, TensorFlow's object detection API is a very powerful tool that makes it easy to construct, train, and deploy object detection models. In most of the cases, training an entire convolutional neural network from scratch is time-consuming and requires large datasets. This problem can be solved by using the advantage of transfer learning with a pre-trained model using the TensorFlow API. There are many different versions detection models trained on MS COCO datasets, and we have selected 2 models to test our project. The selection of these models is based on MAP, which is mean average precision. It indicates how well the model performed on the COCO dataset. Generally, models that take longer to compute will perform better. Once the object is detected in image frame, it then crops image and extracts only object's frame, which is further processed to recognize dominant color in the object frame. So as you can see from the images I'm providing now, the traffic light is circled out by a rectangle. A similarity rate of the traffic light recognized by the model is labeled nearby. The accuracy is pretty good because for of our tests, this model can precisely recognize where the traffic light is. In addition, once the program knows where the traffic light is, it will use a color detection function, which is mainly from CV2, to determine if the color of the traffic light is red or yellow or not. If it is, a text stop will be placed on the left upper corner, and if it is not, a text go will be placed instead. These are all we did for this capstone project. Hopefully everything goes well, and thanks for watching.